Hello and welcome, everyone. Have you ever needed to find the angle of a right triangle when you know the lengths of the sides? Maybe you're working on an engineering project, or you're just solving a math problem. The inverse trigonometric functions are the tools we use to go backwards in trigonometry. Today, we are diving into these functions and understanding how they help us find angles based on the trigonometric ratios. In simple terms, an inverse function does the opposite of what the original function does. For example, sine takes an angle and gives us the ratio of the opposite side to the hypotenuse. The inverse sine function, denoted as sine inverse or sin to the power of -1, does the opposite. It gives us the angle when we know the ratio. But we can only define these inverse functions for certain domains and ranges. Let's break it down further, step by step. To begin, let's review the basic properties of the 6 main trigonometric functions: sine, cosine, tangent, secant, cosecant, and cotangent. Each of these functions takes an input, typically an angle, and returns a ratio of two sides in a right triangle. For example, the sine function takes any angle and gives a value between -1 and 1. But here's the catch: sine, cosine, and other trigonometric functions aren't one-to-one over all real numbers. That means if we don't restrict their domains, they can't have a unique inverse. So, we have to restrict the domains of these functions so they become one-to-one. For example, the sine function's domain can be restricted to the interval from -pi over to 2pi over to make it one-to-one. This gives us a valid inverse function. Let's now look at how we define the inverse functions. Let's start with the sine function's inverse. The inverse of sine is called sine to the power of -1 or arcsine. This function allows us to find the angle whose sine is a given value. The domain of sine to the power of -1 is restricted to the interval from -1 to 1 because those are the only possible values for the sin of an angle. And the range? Well, for the inverse sine, the range is from -pi over 2 to pi over 2, which represents the angles where sine is 1 to 1. For example, if sine to the power of -1 of 1 over 2 equals y, then sine of y equals 1 over 2. We know that sine of pi over 6 equals 1 over 2, so the angle y equals pi over 6. This is how we can find the angle corresponding to a given sine ratio using the inverse sine function. The graph of sine of x looks like a wave, and the graph of sine to the power of -1 of x is its reflection over the line y equals x. Pretty cool, right? Next up, we have the inverse of the cosine function. We call this function cosine to the power of -1 or arccosine. Just like with sine, the cosine function is not one-to-one over all real numbers. So we restrict its domain to the interval from 0 to pi, which makes it one-to-one and allows us to define an inverse. The domain of cosine to the power of -1 is also from -1 to 1, and the range is from 0 to pi. Why? Because when the cosine function is restricted to this interval, each value of x gives a unique angle between 0 and pi. For instance, if cosine to the power of -1 of 1 over 2 equals y, then cosine of y equals 1 over 2. And we know that cosine of pi over 3 equals 1 over 2, so y equals pi over 3. The graph of cosine of x is a smooth curve, and the graph of cosine to the power of -1 of x is again a reflection over the line y equals x. By the way, we use cosine to the power of -1 of x often in geometry and physics to find angles when we know the cosine ratio. Now let's talk about the inverse of tangent, which is tangent to the power of -1 or arctangent. The tangent function has a domain of all real numbers except for odd multiples of pi over 2, because those points lead to undefined values. So, to make tangent of x 1 to 1, we restrict its domain to the interval from -pi over 2 to pi over 2. This means that tangent to the power of -1 of x will give us an angle between -pi over 2 and pi over 2, which makes it a unique inverse. For example, tangent to the power of negative 1 of 1 equals y, where tangent of y equals 1. And we know that tangent of pi over 4 equals 1, so y equals pi over 4. The graph of tangent of x has that familiar zigzag shape, and the graph of tangent to the power of negative 1 of x is a reflection of that over the line y equals x. Let's move on to secant, which is the reciprocal of cosine. The inverse of secant is denoted as secant to the power of negative 1, or arcsecant. Its domain is r minus 1, 1, because the secant of an angle can never lie between negative 1 and 1. The range of secant to the power of negative 1 is from 0 to pi, excluding pi over 2, which gives us the principal value branch. This is useful when we want to find an angle given the secant of the angle. For example, secant to the power of negative 1 of 2 equals y, where secant of y equals 2. We know that secant of pi over 3 equals 2, so y equals pi over 3. The graph of secant of x is a U-shaped curve, and the graph of secant to the power of negative 1 of x is again the reflection of this curve over the line y equals x. Let's quickly revise what we've learned today about inverse trigonometric functions. We started by understanding that each inverse trigonometric function is the reverse of its corresponding trigonometric function. The sine, cosine, and tangent functions can be inverted when we restrict their domains. We also learned the principal value branches for each inverse function, which gives us the standard range of angles. These functions are extremely useful in calculus, geometry, and engineering. They allow us to find angles when we know the ratios of sides in a right triangle or other geometric context. And that's the foundation of how we understand and use inverse trigonometric functions in math. See you in the next topic.